Okay guys, today I think we're going to talk a little bit about some antenna topics. So continuing on with some of our wireless ideas. So let me get started. I got a lot of show and tell for you today, so we'll kind of do that. Alright, so without further ado, let's talk some antenna topics. So what is an antenna? Well, an antenna is sometimes, like one of these guys here, an antenna is sometimes called a radiator, a conductor. It is really just a wire. Now we'll actually see a couple of examples here in a second, but it's really nothing more than something that does conductive material, or something that can convert or accept electrical energy and then convert it to RF energy. I have actually used, and we've seen used, coat hangers all the time. When you don't have an antenna, stick a piece of wire in there. So that works pretty well. So the way that this works is that when I have a radio, kind of like this guy here, so we know we have these antenna ports here. What comes out of here, what comes out of the radio, is electrical energy. So a radio generates electrical energy. And when we hook up an antenna, not unlike, no, where'd they go? Where'd they go? There we go. An antenna, like this here. Then what happens is the electrical energy hits the antenna and is converted to RF energy. So the electrical signals exist at the surface of the conducting material, and so when they hit the antenna through this mystical, magical physics property called skin effect, the RF energy becomes radiated into the environment. So the whole point of an antenna is to convert electrical energy to RF energy. Now, one of the things to remember about antennas is that the physical dimensions of an antenna are directly related to the frequency that you want to transmit. So if I take a look at, say, this guy here, and we'll zoom in a little bit there, this guy here and this guy here, these are both 802.11 antennas, but as we can see, they're different sizes. That's because the larger antenna is designed to work with lower frequencies. So this is a 2.4 gigahertz antenna, and this is a 5 gigahertz antenna. Now commonly, the wires that we use are about half the length of the wavelength. So it's very common to have an antenna that's either a multiple of your wavelength, or if your wavelength is here, then half of the wavelength, sometimes even a quarter of the wavelength. But there's some direct proportion that we deal with when we start building antennas, and we look at the wavelength that I want to use, and then the actual size of the antenna that might be appropriate, or that can be used in a particular environment. So a half-wave dipole is a very common example of an antenna that you might see deployed in a modern communication environment. So there's a couple of things that we talk about when we deal with antennas and RF systems. An antenna, as you can see, there's nothing to it, right? So there's nothing that we add to increase the signal strength except the antenna. So this is what we call a passive device. If I was to add an amplifier or something like that, this would be an active device. Now, as I said, the height is directly related to the wavelength, but this antenna here, is meant to be used with the same wavelength, so the same frequencies that this guy is here. So this is actually just a multiple of this particular antenna. But the size is directly related to the frequency or the wavelength that I want to use. So we'll talk a little bit more about this here in a second, but it's not always that you can just put on any old antenna and get the best possible performance. Now the shape of the antenna, I've been waving these guys around, but the shape of the antenna makes a big difference. So when I take something like this guy here, all right, this has a completely different shape. This is called a patch antenna. And, oh, I forgot to bring it out. Bear with me one second. There we go. We look at an antenna like this guy here. We can see that this has a completely different shape than all of those other ones. And we'll just put that down for a second. Okay. There is also this idea of the dimensions that you want your radiation pattern to go in. Are you really trying to focus your energy all over the place? You know, maybe this sort of three-dimensional beach ball sort of thing. You're trying to go for that. Are you focusing the energy in a particular direction? So these are things to think about when you're generating your energy. Are you worried about one dimension, or you want to get it out, but you also want to get it up or even down in your propagation? All right, antenna types. We got a couple of antenna types here. Omnidirectional. Omnidirectional means that you're radiating your power in all directions. So what we've got here is an omnidirectional radiator, and it looks just like a wire, and that's really what it is. So when I have electrical energy that's converted to RF, what that means is that it's going out in all directions from this particular antenna. Now this is as opposed to something that might be more directional. So the shape of this antenna, you can see that it's got some thickness here. The shape of this antenna means that the radiation is going to be pushed out in a particular direction. That doesn't mean that there isn't also radiation on the back side. So this antenna was meant to be mounted on the wall, and we've got radiation going out in that particular direction. But there is still some here on the back side. Now, some antennas are meant to push energy a lot in one direction. So those would be antennas like this one here. This one is really designed to focus the energy in a particular direction. And you can see that if I take the cover off of this guy, you can see that it's sort of really designed, you can see that pretty well here, designed to push the energy or focus it in a particular direction. So, examples of directional antennas include Yagi's, horn, grid, patch antennas like we were just looking at on the small square there. Directional or omnidirectional antennas include things like this guy here. This is a dipole, and then we've got smaller ones, half-wave dipole, quarter-wave dipoles. So that's probably the most common. And then, of course, we've got larger versions of these guys. Really, what we're dealing with when we change the dimensions of the antenna for the same frequency is we're looking to get gain out of this. All right, so remember that the radio creates the electrical energy and then sends it out to the antenna. The antenna now becomes what we call the intentional radiator. So at the edge, it becomes the radiator, but the RF energy by specification goes out to what we call the intentional radiator, which is right here. That's where it stops. And if you think about the RF specifications, we really have no idea what antenna somebody's going to put out here on the end. And so the specifications stipulate the power that's permissible here at the intentional radiator, at the edge of the radio itself. The antenna is actually what we put out, we'll put on the end, and that tells us how we want to focus the energy. Now there is this theoretical radiator that's out there called an isotropic radiator. Theoretically, in an isotropic radiator, the energy is radiated in equal directions. So if I took my little dipole here again, and I imagined putting a beach ball over this thing, so the beach ball is all the way around and then three-dimensional, so like this, that's sort of equal radiation in all directions. Well, that's not actually what we get. We get actually this sort of decreased size on the top, but it sort of extends here. So the radiation pattern that we actually get is more like a squashed donut, that's what we call it, around an omnidirectional radiator like this. So the radiator that could radiate in all directions is called isotropic. The best example that we have of an isotropic radiator is the sun. Now, antenna gain. Gain is a measurement of an increase in performance. So we talk about gains in weight, we talk about gains in signal strength, we talk about gains in performance of all kinds, but really what we're doing is we're comparing what we had to what we have now. So I could compare the performance of this antenna to the performance of an antenna like this one. I could compare maybe inappropriately, but the antenna performance here and the antenna performance on a guy like this. The point is that you come up with a proper measurement. So if we compare the isotropic radiator, that equal radiation in all directions, to a dipole like this is a 5 gigahertz dipole, then I might say, well, compared to the isotropic radiator, this one performs in a certain fashion. So because it's not radiating equal in all directions, I actually get a little bit farther out this to the sides maybe. And so that's dBi, comparing this antenna's characteristics to a theoretical isotropic radiator. But I could also compare this antenna directly to another antenna that performs in similar fashion. So I might compare an antenna to a dipole, and so that would be dBd. Okay. Now polarization is an important idea. Polarization is the direction of your antenna. So if I take this antenna and I'm talking to another radio that's also got an antenna, I want the polarization to be the same on the two. So what I don't want is this sort of thing, because the antennas are designed to radiate energy in a particular direction. So what I want to do is match the polarization of the wave. You've talked about you've heard about polarized sunglasses. It's the same idea. Wavelengths propagate in a particular direction and in a particular sinusoidal waveform shape. So if I change the polarization even a little bit, it can make a difference on my reception and my transmission capabilities. So we want to the extent that it's possible, we want to ensure that the antennas are polarized in the same way. This is one of the reasons why the antennas in a laptop are in the screen, because we know that they're going to be vertically polarized like most of our antennas. Now, radiation pattern is an important thing to remember. A lot of times we just say, well, these are the antennas that the radio came with, or the AP came with, I'll just use those. But sometimes that's not exactly what we want. Sometimes we want to push the signal out a little farther. Sometimes we want to push the signal in a particular direction. So we buy an antenna. What should come along with your antenna, or when you're doing your shopping, is some indication of how the antenna is going to perform, what the antenna is going to give you in terms of radiation pattern. So you should get an idea of how the radiation propagates out horizontally, but also vertically. So we want to know that. And so sometimes it's very appropriate to put a directional radiator out there, but sometimes it's very appropriate to have your omnidirectionals. Now when you're dealing with radiation patterns, we have this thing called lobes, like earlobes, but lobes. So the main lobe is where a majority of the power is generated. So if I point an antenna at you, then the energy is going to come straight at you. And the side lobes are going to be sort of where a 50% decrease in the power might be. So if I point right at you, so if I aim an antenna right at the camera, most of the energy is going to go right this way. But some of the energy is going to go out here. So the main lobe is defined by what we call the 50% power point. So kind of this right here and right there. So when I get out to these points, I lose about 50% of the power, or minus 3 dB. So out to these points, so that's the boundaries of our main lobe, and that's also where the side lobes live. So you can have this sort of idea of around an antenna like this, where most of the energy is, and then outside of that we have the side lobes. So radiation pattern and the lobes of the signal strength, a lot of times you'll see them, they look like sort of amoebas around the antennas. Those are the radiation patterns and the lobes of the signal strength. Now beam width is a measurement of that angle. So when I look at the side lobes and then, or maybe the width of the main lobe, right, that is the beam width of my radiation pattern, or the beam width of a particular antenna. And what that gives me an idea is where most of the energy is concentrated, and maybe how far out I can be and still receive that energy. Obviously, the idea of beam width and lobes are not as appropriate for omnidirectional radiators. It doesn't make a whole lot of sense because it's all around the antenna. But when you deal with directionals, you certainly want to get an idea of the beam width that you might be dealing with. Now, bandwidth is a measurement of the frequencies over which an antenna is expected to perform well. Now, I said earlier that I've used spectrum analyzers and things like that, and we couldn't find the antenna, or we didn't have the antenna we needed, so we just hook up any old conductor that we have. And that's true, but I can't expect the best possible performance when I'm dealing with that. Excuse me. So, what I want is the antenna that's appropriate, or most appropriate. This is a 2.4 gigahertz antenna. Does it mean that this won't work with 5 gigahertz? No, it'll work. Might not work as well as, say, this one right here, because this one's designed for 5 gigahertz. And I can flop them, right? So that's the idea. You want to pick the antenna that's appropriate for the frequency that you're using. That's bandwidth. But, you know, when you're trying to get RF signal propagation, any port in a storm. Fresnel zone, or Fresnel zone, is an area around the antenna that is where most of your energy is concentrated. So you can sort of think of this as, if I'm directing energy at you, so I have a directional antenna again, most of the energy is concentrated. Okay? Now, this, if we stay inside the beam width of the antenna, you can expect to have pretty good signal reception. But what happens if I start putting obstacles in between here? Well, the Fresnel zone is this sort of conical shape around the propagation of the antenna, or around the propagation of the signal. And if I start blocking this cone between me and you, I can start interfering with the signal. That should sort of make sense to you. Well, it turns out that this thing called the Fresnel zone defines this cone around the antenna. Now, it's directly related to the kind of antenna that you have, the distance we are apart, and the frequency that we're using. The idea is that within the Fresnel zone for directional antennas, you can have a certain amount of occlusion of the zone. 20 to 40% you're probably okay, but the minute you get above those numbers, you start to have too much blockage in your line of sight, and that's a bad thing even if you have a high gain directional antenna. So you sort of want to stay away from this. So some funny stories about this include things like, well, people put up antennas and then they grow a bunch of trees around, and all of a sudden the trees are in between the antennas, and so that creates a problem. When I was in the Navy, we had a thing called the Fresnel zone, or the Fresnel lens, on the back of the aircraft carrier that the pilots could only see if they were in the right glide path when they were coming into land. Now, when your signal actually propagates, right, so you can sort of imagine this signal propagating between the source and destination, over time the signal degrades. Now, it can degrade for a whole bunch of reasons: atmospheric effects, temperature, water conditions, all those kinds of things. But it attenuates over time, or gets disrupted. And we just call that free space loss. It's just what you started off with compared to what you have at the end. Now, so a couple of years ago, there was a big to-do about cantennas. So let me grab another one for you. Sorry about that, I keep disappearing off the camera, but here you go. So everybody wanted to take Pringles cans, right? Pringles cans, this is not a product placement, by the way. So Pringles cans to make antennas out of it. So that was a big deal, and on the websites you would always see everybody blacking out their eyes. And that's because you can't just simply take any old antenna and plug it into an access point, because vendors make their equipment, and it's designed to be used with a particular set of antennas. So you can't just plug in any old thing. Why? Because you violate the power restrictions with unlicensed devices. By the way, my personal favorite was the baked bean can. I think they always outperform the Pringles can. So there you go. There's a DIY tip for you. Baked beans. All right. And the reason that we worry about these kinds of things is because, remember that we're talking about the unlicensed spectrum. So the unlicensed spectrum has power limits. Well, what are some of the powers that we're worried about? Well, effective isotropically radiated power, EIRP. That is the power at the output of the antenna, not the intentional radiator, but the antenna. So, what do I do with it? I take an access point and I plug in an antenna to it. I have the power right here, and then I have the power out here. So EIRP is a measurement of how much power this thing, the antenna itself, is actually putting out. Generally speaking, we have some limits here. If I'm limited at the intentional radiator of 100 milliwatts, a very common limit. Okay, where were we? Let's see. So we were talking about EIRP. And so when I'm dealing with EIRP, I start with my power at my intentional radiator. So these guys have an output power of 100 milliwatts. Now 802.11a and 802.11n have some different power output requirements depending on the frequency that you've chosen. And very commonly the antennas that I might use inside have restrictions on the gain. So you're not going to put in those dish antennas and focus major amounts of energy down the hallway and be able to cook bacon in everybody's office. So there's a limit here, and what we want to limit our EIRP to, the power that the antenna itself is actually putting out, we want to limit that to about 1 watt. Now, the FCC loosened up a little bit, and then recognizing that if I'm going to put a higher gain antenna on here, it's probably for outdoor use. And so I've got a top end on antennas over a 6 dBi gain of 4 watts. But 1 watt is a pretty good rule of thumb. And what that means is that if your antenna is higher than that, then you actually reduce the output power of the intentional radiator. Whoa. All right, so let's talk a little bit about voltage standing wave ratio. So another acronym, we've had VSWR, and now we got, we had EIRP, and now we got VSWR. Voltage standing wave ratio is a measurement of the impedance difference between two circuits. Well, without getting really complex, when you're dealing with an AC circuit, we have resistance that we worry about, we have capacitance, and we have inductance. Those three things together give us something called impedance. And it's just an electrical characteristic. And what you don't want to do is have a mismatch in your voltage standing wave ratio between two systems, meaning that you've used the correct connectors and conductors and antennas appropriate for a particular application. So if I go back to my AP again, and I use something that was designed for it, so I've got my antenna and I've got my connector right there on the end of the conductor, and then I've got my wiring itself. They will all have the same electrical characteristics. Now when you start to get a little nutty, right, you start to build systems that might be outside, things of that sort, you might run into some difficulties. Well, what might that look like? Well, what if I put on something like this? Now you can see that on the end of this guy here, the connector is completely different than something like this, right? They don't go together. So this is an antenna that's designed to be used for a particular application. And I would actually have to get out some adapters, things like this guy here, to actually get this sort of stuff to work. More than that, I might actually need another kind of cable. Bear with me one more second. so look at these guys here. So if I was to actually try to extend the antenna, maybe have an antenna that goes outside of my window here, and I might use it with somebody here. You can see that I haven't shown you the back side of this. There's a big old connector right there. Okay. So when I want to run cable like this to outside, I want to make sure that my impedance readings are the same. So when I look at a cable like this one here, a lot of times the impedance readings are right on the side. Commonly, coaxial systems are either 50 ohm or 75 ohm, which also means that not only do I have to pay attention to whether or not the systems are designed to be working together, am I using the right conductors and cabling to connect all this together? If I use the wrong ones, then I wind up with something called a voltage standing wave ratio that's off what I want it to be. A good ratio is 1.4 or 2 to 1. I like to stay near that 1.4 number. If I start to get higher than that, a bigger mismatch, then I can actually have reflection back into my system. So you may have heard of things like return loss or reflections internally, and what that means is that some of your signal is bouncing back maybe to the radio, causing damage. So the powers that we talked about, powers to keep track of, are things like power at the intentional radiator, power at the output of the antenna, and then we've got, so that's intentional radiator power, commonly measured in milliwatts, EIRP out here around the antenna, and then we also want to keep track of things like what were my losses in my conductors or my connectors, and all of those conductors that I might be using. How much did I lose of my signal strength? Now before I go, I talked a little bit about earlier about these antennas looking very fancy, but actually they're just conductors. So let's take the cover off one of these guys, and I'll bring this in a little bit closer, and you can see that I've got a little styrofoam piece here on the end just to keep it in place, but you can see that over the length of this antenna, it's really just wiring maybe in a fancy shape. So there's a solder at the bottom there, but really it is just a sort of conductor. That's all it is. We can get this back together here. There we go. All right. So good design for your systems. There's a reason why we put APs up on the ceiling. So you want to have your AP to be the appropriate height above ground, or really what we care about is where the antennas are. Just because you can see the AP doesn't necessarily mean that that's where the antennas are. So the antennas are going to be located in a way to give them the best possible signal strength, best possible radiation around the area. Appropriate angle between sites. If I am using antennas like these guys here, and I'm going to be pointing them at each other, I don't want to have this sort of height mismatch between them, right? So this is, you know, an example where I want to get my line of sight where I need it to be, my beam width fixed properly, and my frontal zone all straightened out, right? Okay. I want to use the proper antenna for the application. Do I have the right size for the frequency? Do I need something that's a little higher gain? Recognizing that the minute I go to higher gain, I change the radiation pattern. They're not the same, even though they look like they're in the same shape. By the way, just because you have these antennas doesn't necessarily mean that you get a massive performance improvement because you went to a larger antenna. This is just a 3 dB gain antenna. So it'll give you an improvement, but it might not give you the thing that, you know, the performance that you need. You might actually want to go with something that's more directional. You want to make sure that you take care of your line of sight, clear your frontal zone of occlusions. The same polarization, right? So we're worried about things like this, right? We want to make sure that they're lined up the same way. Watch your power levels. if you've got one of those antennas that's pushing that signal strength out to 1 watt EIRP, you want to back off on your internal power. If you're outside, watch the wind. Make sure that you've got the appropriate antenna. That's one of the reasons you go to a grid antenna when you're outside, because it has less wind resistance. Alright, and maybe just to close up here, I'll just point out that we've got all kinds of different antennas depending on the application. If you take a look at one of these guys here, this is antenna that you kind of see. I'll get real close. This is an antenna that you sometimes see on vehicles, and when you look at some of the older cards that we have, so this is an Orinoco card, but right on the end there, let's see if you can see that, there's an N-type connector. So I would take an antenna like this one, plug it into the radio with that style connector, and I would get an improvement. Because you can imagine this PCMCA card, this guy here goes into a laptop, but the antenna is right inside here. So this little port gives me an opportunity to connect to something external, get an improvement in power. This antenna here was an old frequency hopping antenna. You would plug these right into your laptop card, and then you would connect these to the side of your monitor screen. So that was our early generation wireless connecting. Well, I think that'll about do it. Thanks very much for watching. May your packets always reach their destinations, and hey, this is networking. You can do this.